Last time we took a look at how to create just a simple class. Okay. So for example, we created a class called student, if you remember. We discussed the convention, what's the naming convention in C#. Okay, every language has its own naming convention. So we discussed that class names start with uppercase. Okay. If you're creating any private variable inside a class, that starts lowercase. Okay. All the public fields or public methods start with uppercase. Okay. And the default in C#, if you remember, was private, right? Okay. So for example, we created 5 fields, and our first field was, for example, string first name. Okay, unlike C++, where we use underscores to separate out multiple words, here we write it as a continuous thing, but each following word starts uppercase. Okay. So what's the default visibility as I create this? Private, right? Okay, so we expose each private field through tiny get and set functions, right? And we discussed that we can write it in the Java style, or we can use the C# property style. What's the property style? What does it look like? We say public string. Remember, all public fields by convention start uppercase, right? So that's why we will make it first name with a capital F. Then inside it, there will be a get part, return first name, and there will be a set part, first name equal to value. Okay. So then we also saw that rather than us typing all of this code ourselves, what was the shortcut to it? Once you type this black part over here, then using Visual Studio, you right-click on it, refactor, encapsulate field, and it will automatically type the blue part. So it makes our life a lot easier, right? So very similarly, we created, so this is one field, right? The private is first name, and the public property is first name with capital F, right? Okay, very similarly, how many fields did we create over here last time? Okay, we created a field called last name. We created a field called ID, test1, test2, right? So let's pretend every student has these 5 fields, right? Now, typically, once we create a class, remember we discussed classes like a template. Okay, nothing exists in the memory of the computer unless we create an object of it. So for example, if we are creating a university application where we have 6,000 students, we'll create 6,000 objects of it. Each one will have a separate first name, last name, ID, test1, test2, right? So one of the important things to understand is, as we run a program, what gets created in the memory, if somebody, remember last time we wrote a small program to test this code, and our program was something like this. Okay, we created a button handler. Okay, meaning if you click on it, it will call that function. Okay, and in this button handler, we created one object of the student class. So our code looked something like this: student S1 equal to new student. Then we did S1 dot first name equal to whatever S1 dot something, S1 dot, right? And then we called something like this, message box dot show, and something grade equal to something plus S1 dot
compute grade.
Did we write the compute grade last time?
Yes.
Okay, we did. So let me add one more function over here that we wrote. we also wrote one function, public string compute grade. And it does some computations and returns, for example, A minus, B plus, or whatever the case may be, right? So our test code was something like this. This was the red part was our test code. Okay, so one of the important things for us to understand is, okay, why are we writing this new student? It's, at first, you know, for those of you new to this kind of programming, it may be confusing. What is student S1? What is this new student? Okay, what happens when we say S1 dot first name equal to Bill? What does the computer do, right? What happens once we say S1 dot compute grade? And I forgot, anytime we call a function, we have to have parentheses, okay? So to clarify these fundamental concepts, okay, so let's take a look at a computer. See, whatever program we write has to execute on a computer, right? What is a computer? A computer is a CPU connected to memory, and this is what we call RAM, for example, random access memory. So for example, when you go to buy a laptop, you know, they sell you with 8 gigabyte of RAM or 16 gigabyte of RAM, right? So that's the memory, right? There's also a hard disk connected to our CPU. So for example, all of our files are stored over here, right? Now, first important concept you need to know is that if we wanted to run a program, it cannot run by sitting on the hard disk. It has to be loaded in the memory of the computer. Once it's got loaded, then the CPU has all the circuitry to add, multiply, subtract, and so on, divide, take the cosine, take the square root. All that circuitry is inside the CPU. So once the program gets loaded, the CPU brings it, goes to the memory, brings the instruction, and executes it, right? Okay, so if we write, for example, a C# program like this, okay, if we, in the beginning, remember, as we are typing it through Visual Studio or through whatever editor we are using, here's our C# program. Okay, so as I mentioned, it cannot run by sitting on the hard disk, okay? So how do we run it then? Okay, if we load C# program into the memory of the computer somehow, okay, the problem is it will still not be able to execute because CPU does not understand C#. CPU does not understand C, C++, C#, Java. What language does the CPU understand? Machine language. Okay, so this will still not work, okay? So what do we have to do? This is where we use a compiler. Compiler is a special program. So before we load it into the memory, we pass our program through what we call a compiler. Compiler's job is to convert whatever language we have into the machine code. Okay, so for example, on the Windows operating system, it will produce a file with an exe extension, right? Now if you double click on this exe file, then what the computer does it, or what the operating system does it loads the exe file into the memory. So this is all machine code now. Okay, once it's loaded in the memory, now the CPU can bring one instruction, execute it, go to the second instruction, bring it, execute it, and can execute the whole program, right? Okay, the other thing to understand is, as we are running this program, it will need additional memory, okay? For example, let's forget C# for a second. Let's go to the plain old C language. So suppose in the C language, you wrote some kind of a main where you said something like int a equal to 5, int b equal to 7, int c equal to a plus b. Okay, let's take a look at this very, very simple program that you wrote in C language. Okay, Now, if we wanted to run it, can we simply load it into the memory of the computer? No, we have to first compile it, right? So once we compiled it, it will, so there are 3 instructions over here. These 3 instructions will get converted into machine code, maybe 3 instructions, maybe 5 instructions, maybe 6 instructions. Machine code, one high-level language may get translated into 2 or 3 or more machine-level instructions. So anyway, whatever that translation was, okay? Once this program is converted into the machine code, now if we try to run it, take a look over here, what will happen as the CPU tries to execute it, okay? See, it has to declare some memory to store A, okay? So in this memory, we have 2 special areas. One is called the stack area, one is called the heap area. Okay, both of these are used to allocate memory as our program executes, okay? So for example, anytime we call a function, including the main, if we declare some variables, the memory for those comes from the stack area, okay? So all local variables, meaning variables that are declared inside a function, so variables declared inside a function, these are called local variables, okay? The memory for these comes from the stack area, okay? So all local variables are allocated on the stack, meaning the memory for those comes from the stack area. So as the computer is executing, it will take a look at int A, for example. So it will allocate some memory over here for variable A, okay? Then A equal to 5, it will store 5 over here. Then int B equal to 7, it will allocate memory for B. B equal to 7, allocate the memory. Int C, so it will allocate memory for C. C equal to A plus B, so it will go to wherever A was stored, wherever B was stored, so it will store 12 over here, okay? So what happens to the stack area once the program ends? Do we need this memory? No. So the machine code that was generated over here will automatically clean up the stack, meaning this will go away as soon as the function where these were declared ends, okay? So stack is cleaned automatically. As the function ends, where those variables were declared. So those variables which were declared inside that function are automatically removed from the memory, okay? So that's one concept you need to know. So for example, let me give you another example. At some point in time, okay, we call a function f1. Okay, and suppose we write void f1, okay, and say int x equal to 5, x equal to x plus 2, and n. Okay, so now let me modify this program to look like this. Okay, in the main, we call this function f1, and what does it do? Declares a variable called x, increments it by 2, and then finishes it. So now let's take a look how this execution will go through. Okay, so as we started to run this program, just like we discussed, A, B, C will be allocated in the stack area. So there's A, there's B, there's C, right? A will be put 5, B will be put 7, C equal to A plus B, 12. So now we call this function. As we call this function, take a look over here, precisely at that point in time, what will the computer do? Allocate memory for X. So the X will be allocated somewhere in the stack area. Okay, why will be allocated in the stack area and not the heap area? Because
It's a local variable.
it's a local variable. It was declared inside this function. Okay, then x equal to x plus 2, so makes it 7. The computer will it will put 5, then it will change 5 to a 7, right? Now what happens once this function ends? What will we lose?
The local variable.
Just the local variable x. So stack is automatically cleaned. So whatever variables we had declared in the stack, only the x will be removed. So this x will go away as soon as this function ends. Now we go over here, we finish the function. As soon as we finish the main function, what will happen to A, B, C?
Okay.
They will be removed. Okay, so that's how the stack works. Okay, now let's come to the heap area. Okay, all programming languages these days, such as C, such as C++, Java, C#, Python, and so on. Okay, all programming languages allow us to use the stack memory area as well as the heap memory area. Okay, now stack you already saw. You as a programmer do not have to worry about the stack. You simply declare some variables. The computer will automatically allocate memory. Once the function ends, it will automatically remove that memory. So it's automatic, right? So what's the purpose of the heap? Okay, and how we as a programmer can use the heap? And the answer is, heap is a large memory area. Okay, depending upon the operating system, it's huge memory. Okay, for example, if we are using a 32-bit operating system, you know, if you go back to Windows XP as an example, which is a 32-bit operating system, theoretically speaking, the heap space is 2 raised power 32 bytes, which translates to 4 gigabytes. Okay. Which at one point in time we thought it was huge memory, but today we think it's tiny memory, right? Okay, what if we have a 64-bit operating system? Okay, so technically speaking, how much is the heap space available to us? 2 raised power 64 bytes. Of course, part of the memory is taken by the operating system. So generally speaking, half the memory is taken by the operating system. So in a 32-bit operating system, 2 gigabyte is given to us from the heap space as a programmer. Okay. Very similarly in the 64, I mean, this is such a huge memory as of now, so that we don't have to worry about it. So in short, as far as you guys are concerned, if you can just remember one small thing, and that is, if you wanted large memory as your program executes, you should use the heap area, okay? Now, how do we use the heap area, okay? What do we have to do over here so that the variable gets created over here, okay? So now let me give you one more concept. Okay, for example, in C#, very similar to Java and other languages, okay, there's a concept of a value type and a reference type. Okay, what is a value type? Okay, value type, first of all, gets created on the stack. Okay, so now hopefully you know what is a reference type as compared to over here. It will get created where?
Heap.
Gets created on the heap. Okay, so what is an example of a value type? Okay, all these standard data types, so all the standard built-in data types, okay, such as int, double, character, byte, float, and there are a few others, unsigned byte, unsigned character, and so on. So anyway, these will always be created on the stack, right? So for example, if I declare a variable int a equal to 5, where will it be created? On the stack. Two reasons. One, it's a local variable. Second reason, it's a value type. Okay, value types always get created on the stack. What is a reference type? Okay, first of all, it gets created on the heap. Okay, so for right now, we'll be introducing more reference types as we go along. So all class objects get created on the heap. So class objects is an example of a reference type. Okay. So now let's come to over here. So second, so a related question: how do we know that something was going to be created on the heap and something was going to be created on the stack? Anytime we declare a variable, and if the variable is a standard data type such as int a, or I could also say double b equal to 2.5, right? A decimal number is created as a double data type. Okay, so that's a standard data type. Both of these will get created on the stack. Okay. Anytime we use the new keyword, okay. So anytime we use the new keyword, that's a hint to us that that variable will be created on the heap. Okay. So take a look at the student now. Student S1 equal to new student. So where will the memory for S1 come from? Heap. Okay, so now further, this student S1 equal to new student actually is two separate statements, okay? Even though people write it as one statement, okay, think of it this way, this one as student S1, and then S1 equal to new student. So technically, student S1 equal to new student, so student S1 equal to new student is one statement is student S1, second statement is S1 equal to new student. Okay? So now let's try to understand it. The first statement, student S1, is there any new keyword involved over here?
No.
So S1 itself will be allocated on the stack. Okay, see if I draw the CPU. Suppose this is the memory. Okay, this is the compile code. Remember, the compile code gets loaded into the memory. Then let's pretend this is the stack area. Let's pretend this is the heap area. Okay, now let's go. Student S1. So we call this S1 a reference. So S1 will get created on the stack. Okay, because if you, once again, if you take a look over here, the first statement, there is no new keyword. So S1, think of S1 like a pointer, and that's what we call a reference, and that gets created on the stack, right? Then, now let's go to the second statement. S1 equal to new student. Okay, so that means we need to allocate memory for the student. And where is this going to come from? Because there's a new keyword, heap. So now let's go to the heap. How many fields a student had?
5.
Okay, 5. Okay, for example, take a look over here. Is this a variable?
Yeah.
Yes. What about this property, first name? Is this also a variable?
No.
No, it's a wrapper for a get function and a set function. So this is not a variable. The only variable is the first name with the lowercase f. So the main point is the computer will allocate as soon as it executes this statement or this statement, doesn't matter, both mean the same thing. it will allocate memory for first name with a lowercase f, then last name with a lowercase l, then ID, then test1, then test2, okay? Because those are the 5 fields we need for one student. So new student will end up allocating this memory in the heap. Now let's connect the two together. S1 equal to new student, so S1 now will be pointing over here. Okay, so this is exactly what the computer will do as soon as it executes the statement student S1 equal to new student. Okay. Now let's go to the next statement. S1 dot first name equal to Bill. What will the computer do now? Okay, what is first name? With a capital F. It's a wrapper for either a get or a set. So the computer will either call the get or it will call the set. How does the computer know which one to call? If the first name appears on the left-hand side of equal to, okay, then the computer knows somebody is trying to modify. Which function modifies? Set. So now remember, all these get sets are tiny functions over here. So for example, there's a get for the first name. There's a set for the first name. Okay, so as soon as we execute this statement, the computer will go to the set function, so we'll call the set function. What's the code in the set function? Value will be stored in the first name. So which one will be treated as the value over here? Bill will be treated as the value. Okay, so Bill will be stored in the variable first name, which was the memory. So over here, Bill will get stored over here. Right? Okay, so now the question is, what will happen to, in same way if we said last name Baker, for example, then as soon as this is executed, Baker will get stored over here, and so on. Okay, suppose we stored 85, 91, so there was a test1 equal to 85, okay. So anyway, once we stored over here, now let's go to this statement. S1 dot compute grade. Okay, so what will the computer do? Okay, once again, what is compute grade? We had written this as a function, right? So public string compute grade over here. Okay, begin curly, end curly, right? So this was our public function. So now and where will this function be compiled and stored over here? In the stack space, code space, or heap space? See, once again, there are 3 memory areas. There's a code area. There's a stack area for local variables, the standard data types, heap area for the class objects, okay? So when we compile this code, the code for the compute grade function, where will it be stored? Stack area, code area, heap area. Where? Code area, because it's a function. All functions go into the code area, right? So over here, there's a compute grade function. Okay, so anyway, so as we call this, computer will call this. And if you recall, one of the first things we did over here last time was something like double AVG equal to 0.4 times test1 plus 0.6 times test2, right? Okay, so now as we are calling this compute grade function, where will the computer read the value of test1 from? See, because we called it through S1, and S1 is pointing over here, so it will go S1 dot test1, it will read this over here. we will read this over here, right? Then compute the average and then make a decision to assign a grade, okay? Okay, so anyway, to summarize, all simple type of variables such as int, double, character, byte, where do they get stored in? Which memory area? Stack area, okay? All the class objects, so if we wanted to create one student, S1, where will the memory come from? Using the new keyword, the actual memory for all the fields will come from the heap, but the S1 itself, which is pointing to this, will come from the stack. Okay, so now let's take a look over here. Suppose this code was written in the button handler, right? As we discussed, as soon as the function ends, what do we lose? We lose whatever was created in the stack. So what will we lose if we...
S1.
So S1 will be automatically deleted. So now here's the problem. Since S1 went away, this memory is still there, okay? So now, however, we have lost all connection to this memory. So this will be what is called a memory leak, okay? So imagine what will happen if somebody called this 1,000,000 times. You pressed on this button 1,000,000 times. Each time you press, it will allocate one more memory, one more memory, one more memory. As soon as you finish, you lose the connection to it, right? So pretty soon computer will run out of memory, okay? So in a language such as C++, it's the programmer's job to clean the heap, okay? So very briefly, let me show you, if we were writing this code in a C++ language, our code will look something like this. Student star S1 equal to new student. So S1 is called the pointer in the C# terminology. Sorry, in the C++ terminology. Okay. Now if we simply finish this button handler, did not clean the heap, we will have what is called a memory leak. As I explained, this will stay there forever, okay? Unless you shut down the computer, okay? So if you are programming it in C++, you have the responsibility to write one extra line of code over here before you end the function called delete S1. So what does it do? It starts from the S1. So it starts from the S1. So remember, the function hasn't ended yet. It will go remove all this memory from the heap. And then once we end it, S1 will also go away. So all memory will be properly cleaned, right? Now languages like Java and C#, both of them take the approach. Why should a programmer remember to call the delete? See, what if you forgot this, right? And you created a big application where millions of users are using it. In one of these functions, you forgot the delete. What will happen? Over a period of time, the computer will run out of memory and your application will crash, okay? So that's why Java came along. So Java was introduced around 1995. And Java did a few nice things. So let me go over some of those. So next few minutes, I'll compare C, C++, Java, C#, Python to show you what are the major differences between these languages, so that as you program, and tomorrow if you wanted to switch from C# to Python or C# to Java or Java to C#, you have a clear understanding, okay? So let's go. And sidetrack for a few minutes and understand the differences Okay, so I'll try to clarify differences between C, C++, Java, C#, Python. Okay. Okay, so first major difference between all of these languages is we have two types of languages. We have, as a broad category, we have what are called statically typed languages. So statically typed languages. And we have what are called dynamic languages. Okay. Okay. Sometimes we also call these strongly typed. And we call the other category as weakly typed or dynamic data types. Okay. So so C, C++, Java, C# follow in this category of strongly typed languages. Okay. What that means is anytime you create a variable, you have to indicate what is the data type of the variable. Okay. So for example, you will say int a. Okay. Then you can say a equal to 5. Okay. Anytime you try to do a equal to hello, what will happen? See, int is like a whole number, integer, short for integer. So the compiler won't even compile. So this will give you a compiler error. So since it won't even compile, you won't be able to run the program, right? This is okay, but this will generate an error. Okay. Very similarly, if you did double B and said B equal to high, what will happen? Compiler error again, because we said we'll only store decimal numbers. Double is the data type for decimals, right? Okay, so these are, so all C, C++, Java, C#, anytime you declare a variable, you have to indicate what will be the data type, what kind of data will we be storing in it, right? On the other hand, Python, JavaScript type of languages, okay, these are called dynamic languages. You simply declare a variable, you store anything you feel like it. So you can store d equal to 2.5, you can, and there's no such thing as int or double or anything like this in these languages. For example, in JavaScript, you can declare a variable using var, right? I forgot what the Python variable declaration was, but both of them are dynamic. Anyway, you can say d equal to hello, it's perfectly okay. You can say d equal to 223, that's perfectly okay, right? So all of these are perfectly okay in dynamic languages. When the computer is running, it will decide what data we are storing in it, and it will give us full flexibility, okay? However, from a speed point of view, because the computer has to keep checking what kind of data we are storing before it takes an action, dynamic languages typically run slow as compared to statically typed languages, right? So that's why all enterprise application, if you go to any big business these days, they will be running all their heavy-duty processing either in Java or C++ or C# or C, okay? But not in Python or JavaScript. They may use part of it, but not the entire major processing in these languages, okay? So now let's come to, let me slightly clarify the difference over here. Okay, so now C++ is basically an object-oriented form of C language, okay? And Java is object-oriented, C# is object-oriented, Python is object-oriented, meaning we can create classes, we can inherit one class from another. So all these concepts of inheritance, polymorphism, those are all available in all these languages, okay? So the question is then, what's the further difference between these languages, okay? So as for C++ is concerned, okay, as I mentioned, programmer is responsible for cleaning the heap. So that's one difference, okay? Whereas C#, Java, Python, and so on, okay, heap is automatically cleaned. Okay, very briefly how. Okay, let's take a look at our same example over here. Student S1 equal to new student. And suppose this was declared inside some button handler. Okay. So as we discussed, this is actually two statements, right? Left-hand side creates this reference S1. Right-hand side allocates the memory for each student, and then once we assign it, both of them get connected. So that through S1, we can reach any of these fields over here, right? Okay, so the question is, what happens once this button handler code ends? What will we lose? Whatever was created on the stack. What was created on the stack? S1, okay? So if we simply remove this S1, as I was explaining, we have no connection left to this memory. And it will stay there forever, and we will ultimately run out of memory. So in languages like C# and Java, as part of the runtime, so if, for example, in Java, we have what is called the Java virtual machine, which also gets loaded in the memory. Java virtual machine has three main parts to it. Okay, one is the bytecode interpreter. Okay, second part is garbage collector. And the third part is runtime safety environment. Okay, so in order to run a Java program as an example, you have to load JVM, which stands for Java Virtual Machine, in the memory of the computer. So this is not part of the stack. This is part of the code area. Okay, so JVM gets loaded, and JVM internally has three things in it: bytecode interpreter, garbage collector, runtime safety environment. Okay, so this garbage collector over here basically periodically checks to see if an object has a reference count of 0. Okay, if so, it removes it from the heap. Okay, so now let me come to this part over here. So let's go back over here. Student S1 equal to new student. So we allocated S1. As soon as we assigned S1 to this heap area, okay, what Java does is, as well as C#, it has a counter with every object, okay? And because there's one reference pointing to this area, this reference count will be 1. Okay, so now we keep using it. Once we go over here, before we remove S1, because S1 was created on the stack, before we remove S1, we go to wherever S1 is pointing to and reduce the reference count. So this reference count will be reduced to 0, and then this will be removed from the memory. Now this garbage collector, every millisecond, every 5 milliseconds, and we can control it, how soon we trigger it, will keep going to the heap area, will keep checking, is there anything which has a reference count of 0? If it is a reference count of 0, I will simply remove it from the memory. So this way, you as a programmer do not have to worry about it. And you simply write the program, create objects on the heap, and whenever they go out of scope, meaning their reference count goes to 0, garbage collector will take care of us, and we will not have memory leaks. Okay? So compared to C++, where you had to write the delete call over here, okay, there's no need for it in C# as well as Java. Okay? Now both C# and Java, for example, if this is our CPU, if we wanted to run a program, okay, in Java we have to load the JVM. Okay? If you are running C#, the equivalent of JVM in C# is CLR, which stands for Common Language Runtime. Okay. CLR, just like JVM, also has 3 things. Okay, and what are those 3 things? Okay, 2 are the same as Java, meaning there's a garbage collector. And once again, what's the job of the garbage collector? To keep monitoring the heap. If there is something which is not being referenced, to remove it from the heap, right? Okay, what's the third item in CLR? Also safety runtime environment, so that our code does not modify the operating system area and gives us more protection against viruses and so on. Okay. Okay, however, the first part, in case of Java, there was an interpreter involved. Over here, there's a just-in-time compiler. Okay, and let me explain this difference. So this is in C#, and this is in Java. Okay, so let's briefly examine the difference. Okay, if we are writing a Java program, okay, so suppose you created some Java program, you will run it through a compiler. Compiler produces, see, normally if we run it through a compiler, what kind of code it produces?
Bytecode.
Machine code, normally. But in case of Java, it produces what is called bytecode. Okay, so this bytecode, let me make a note, is not machine code. Okay, so it is some binary code, but it is not machine code. So if we try to run it now, if this is the CPU, if this is the memory, okay, if we loaded the bytecode over here, remember I said this is not machine code. So if we loaded the bytecode, will the CPU be able to understand it? No. Okay, so then how do we run a Java program? Okay, so this is where we do not load the bytecode in the memory. What do we load in the memory if we wanted to run it? JVM. Java Virtual Machine. And remember, one part of the JVM was bytecode interpreter. So how will it run it? Okay, bytecode interpreter will read one line of bytecode and tell the CPU what to do. will read another line of bytecode, tell the CPU what to do. So on the fly, it will do the translation, and this is how we run a Java program, okay? What's the slight disadvantage of interpreted code? See, anytime we do not directly compile to machine code, it obviously will run slow, okay? Why? Because there's a translation going on the fly. Every bytecode has to be translated to let the CPU know what it should do, right? Okay, as compared to, let's say, C or C++. So if this is our CPU, if you wrote a program in C or C++, as we pass it through a compiler, what output does it produce? Machine code, correct? The exe in case of Windows operating system. Okay, now can we load the machine code directly over here? Yes. And if we try to run it, obviously we'll run at full speed. There's no translation going on at runtime. Okay? So that's why C, C++ are the fastest languages. If you have a really